Okay guys, so here's our waves, sound, and light PowerPoint. What is a wave? Okay, what a wave is a repeating disturbance or movement that transfers energy through matter and space. Okay, so if you think about it, for example, when you go to the beach and you look out on the ocean or the lake or wherever and you see waves, they are a repeating disturbance. They happen over and over again, and they transfer energy. If there's something floating in a lake or a boat, you see it going up and down. That means that energy is being transferred to that object. Okay? Now, you should have in your PowerPoint, you should be able to see this active link here where you can see the Newton's balls and how they work. That indicates how energy is transferred. Okay? And what it illustrates is that energy can be transferred without moving an object. Okay, now some examples of waves. Okay, one example is a light wave. Here you have a prism with white light going in, and what the prism does is separate the wavelengths of light into what we perceive as different colors, and we'll learn about that as we talk about electromagnetic waves. Sound waves are something that we're very familiar with, okay? And here we have just a picture. What you're hearing, what you hear is the rhythmic vibrations of air molecules. That's what sound is, okay? Earthquakes are generally called seismic waves, and it transmits energy across the surface of the earth. And then we have ocean waves, okay? Here's your regular ocean waves. Here's your devastating tidal wave or tsunami. But both of them obviously transmit energy. This is some energy you don't want to be around.
All right, so when we're talking about mechanical waves, all right, mechanical waves travel through a medium, either solid, liquid, or gas. So transverse waves, all right, medium, so that medium or that solid, that liquid, that gas, moves at a right angle the direction the wave travels. So for instance, like dropping a rock in water, okay? We also have something like this, where you've got that little line moving up and down, all right? Or you could also remember it, am I in the picture?
Mm-hmm.
Okay, like when you're doing your actual wave, all right? Sorry, this is cringy. All right? Or you have compressional waves, okay? We also call those longitudinal waves, all right? So those are the medium, or that's when you have your medium, your solid, liquid, or gas, and it moves in the same direction or parallel of the waves. So like when you guys play with a slinky, which might be a little bit before your time of having a slinky, all right, you are able to pull it out, and then when you compress it back in, you're gonna have it kind of bounce back and forth out, okay? So remember, transverse waves are, you know, your cool wave things, all right? And then your compression waves are when you use a slinky and you push it back and forth, all right? So when we're talking about waves, we talk about different properties in our waves, all right? So for this one, all right, when we're talking about those transverse waves, so we're gonna have that wave again, okay? Mine is not nearly as pretty as normal other waves, drawn out waves, all right? We have the crest, all right, which is the highest point of our wave, so right here, all right? You're gonna have your trough, which is gonna be this point. And then you're gonna have your wavelength, which is the measurement from crest to crest. So your whole wavelength is crest to crest or trough to trough, all right? So that's gonna be your wavelength, and we call that our lambda.
Okay, our next type of wave is a compressional or a longitudinal wave. You can call it either one, compressional or longitudinal. The compression part of the wave is where the matter, the medium, the solid, liquid, or gas is tightly compacted or more dense, and the rarefaction part is where the less dense portion of the wave. Okay, and the wavelength you measure from compression to compression. So let me show you two different ways to draw compressional waves. Compressional waves are often illustrated with a slinky. And one way to draw that is to just draw the slinky as it shows a compressional wave. So when you do a compressional wave on a slinky, okay, as the wave, remember with a compressional wave, the matter is traveling, is moving in the same direction as the energy of the wave. So the matter is moving back and forth the same direction as the wave travel. So this would be a compression right here. This would also be a compression. This is a compression and this is a compression. The rarefaction, okay, or the low density area of the wave is right here, or right here, okay? All right, now, the rarefaction, not rarefaction. Now, the other way to draw a compressional wave is you can actually draw the particles of matter. And this takes a little while, but if you so consider a sound wave. If you could see the air particles when I was talking, what you would see coming out of my mouth, if you could see those particles of air, you would see waves emanating from my mouth, and there would be compressed areas and less dense areas. So these dots represent the particles that make up the air. Okay, and here you can see a compression, 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 and this would be a wavelength. Okay, and this would be another wavelength and another wavelength. And the rarefaction is the less dense area between the compressions.
So right here we're talking about our waves and the energies and how our energy is related to our wavelength, okay? So the smaller the wavelength, the more energy we have, all right? So on this graph here, we have our wavelengths on the side, our big wavelength to our small wavelength, and then our frequency from small to big, okay? So starting here with our biggest ones, all right, we have AM and FM, so you might know those as radio stations, okay? And then you have microwaves, radar, infrared, but I would like you guys to focus on our visible light spectrum, all right? Like our rainbow, it goes Roy G. Biv, i.e. red, orange, yellow, green, blue, indigo, and violet, all right? The farther you go along here, the shorter your wavelength is, the more energy it is. So therefore, your red light is the weakest of your energy, and your violet light is your strongest in your visible light spectrum. Granted, this is normally the amount of sight that you can have with colors, all right? But some people can occasionally see infrared, some people can see UV, all right? It just depends on how good your vision is, okay? And then we have X-rays that are all the way right here. So when you're at the dentist office and they're taking an X-ray of your teeth, all right, they put that little iron thing on you to make sure that it's not going to fry out your insides when they take out photos, okay guys? So make sure that you know that this one has a very, very short wavelength, a lot more energy. And gamma rays, all right, we talked about this a little bit with the nuclear chemistry option, or back in Unit 4, which was forever ago, okay? But you don't want to be hit by gamma rays because gamma rays is what made the Hulk, all right? So shortest wave, more powerful.
Okay, guys, I wanted to say one more thing about the energy present. I like to think of energy kind of in two ways. It's related to amplitude, which is the height of the wave. It's also related to frequency. Let's first look at amplitude, okay? So amplitude is the height of the wave that we're talking about. So I'm going to draw two waves that differ in amplitude, but I'll try to draw them with the same wavelength, okay? So they basically have the same wavelength. If we go crest to crest, you can see that the wavelengths are about the same, but this wave, wave A, has greater amplitude than wave B. And because it has greater amplitude, it has more energy. A simple way to think about this, if these are ocean waves and you're at the beach, you know, walking into the water, which one is going to knock you down, the bigger one or the smaller one? The bigger one is what's going to knock you down because it has more energy. So amplitude is related to the energy.
And we will talk more about amplitude on our next lesson, okay?
Yeah. Now, the other thing that is very much related to energy is the frequency, okay? So let me draw two waves that differ in frequency but are the same amplitude, okay? So, same frequency but different frequency but same amplitude. So I'll draw a wave like this, and a wave like this. Okay, so they're basically the same amplitude, they have the same wave height. Okay, this is wave A, wave B. But if this is a unit of time, say this is 1 second of time, all right, and let's think of these waves as like something hitting you, like something punching at you, right? In that 1 second of time, how many times did you get punched by wave B? Well, you got punched one time. In that same 1 second of time, how many times did you get punched by wave A? Well, there's 1, 2, 3, 4, 5, 6, 7 punches, okay? So in the same amount of time, this wave has hit you a lot more times. So more energy is being transmitted. And that's what's being illustrated here on this graph. As we go down this graph, the frequency is increasing. So, you know, microwaves have a lower frequency than radar, than infrared, than visible light, ultraviolet light, X-rays, and gamma rays. Gamma rays have the highest frequency, so they're hitting you the most in a given unit of time. Okay?
All right. So electromagnetic waves, most of the light energy that we talk about, all of the light energy that we talk about are, instead of our electromagnetic waves, so they are waves made by vibrating electric charges and can travel through space where matter is not present. Okay, so it does not require matter, but it can pass through matter at the same time, okay? So energy is transferred by vibrating magnetic and electric fields, all right? So magnetic fields exist around magnets, all right? And we'll talk more about that at the next unit, okay? And then electric fields surround electric charges, all right? So like your positive and negative and your electrons and all that fun stuff, all right? And then energy carried by an electromagnetic wave is considered radiant energy or light energy, all right? And warmer objects emit more radiant energy than cooler objects, all right? And that makes sense.
Okay, guys, here's a slide on the speed of light, okay? Light is, of course, electromagnetic waves, and the speed of light refers to how electromagnetic waves travel in space. The speed of light sets the speed limit on the universe. Nothing can travel faster than the speed of light, and electromagnetic waves or light travels at 3 times 10 to the 8th meters per second in space. If you're old like me, when I was in school, you know, that number doesn't probably mean a whole lot to you. When I was in school, I learned that light travels 186,000 miles per second. Not miles per hour, but miles per second was the speed of light that we learned in school before the metric system. The speed of light does not, in matter, will depend on the medium. Light travels fastest in space where there is no matter. It will slow down when it passes through a medium like air or glass, solids, things like that will slow it down to a differing degree. And electromagnetic waves are classified by the frequency, and here you see some examples that you can look at.